In this video, I'm going to show you how you can set up an HEC-HMS model and optimize it. When I talk about optimization, I talk about calibration of your hydrologic model. That means that you're going to optimize different parameters and variables that go into your hydrologic model to get a hydrograph that matches your observed hydrograph. So we're going to have observed hydrograph compared with our simulated hydrograph and calculate some statistics to see how good it fits our observed hydrograph. A couple of things before we get started. Number one, the data for this demo is presented to you in the description section of this video, so you can download and follow along with me. Number two, I am not going to focus on model development in this video. I'm going to focus on optimization. So if you want to learn more about how to develop an HEC-HMS model from scratch, I highly recommend watching the tutorial video HMS 101 that I have created before. I link that in the description section as well. All right, with that introduction, let's get started. As you can see, I have HEC-HMS 4.11 open. We're going to create a project and then using that project, set up everything and optimize our model. So let's create a new project. I am going to call it HMS underscore demo underscore 01. All right, and then take a look at this. The unit system that I have is US customary system of units. So create that, the project will be created. Now, the first thing that we need to do is to add a basin to this project. So what I'm going to do, I'm going to go under components and then click on Basin Model Manager and create a new basin. I'm going to accept the default name. If your basin has a specific name, you can enter it over here, create. So you can see that the basin model is created right over here. And when I click on it, it shows some information about that basin. Obviously, right now, no terrain data is connected to my basin. Terrain data is your digital elevation model. So my next step would be to connect a terrain data to this specific model. To do that, you should go under Components and click on Terrain Data Manager. I'm going to add a new terrain. I'm going to accept the name over here and then find the file that has my digital elevation model, and you should know the vertical units of your DEM as well. I know that my digital elevation model has the units of meters. You're going to tell me that a couple of minutes ago, I specified the units of my project to be US customary system of unit. So is that okay if I select this as meters? It is, because HMS internally is going to convert all the units into US customary system of units. All right, let's find the files. I saved them under input data, and this is the raster demo, the demo raster that you are going to have access to as well. The other thing, the data.xlsx is your observed streamflow and observed rainfall, and the outlet.shp is the outlet. Okay, so I'm gonna select the demo raster and click finish, and it will be added right over here, right over here. So although the file is over here, nothing shows under your basin model on this view window. So in order to make it show up over here, you need to go back, click on basin, and then connect your terrain data to your basin. All right, still nothing shows up over here. Click on terrain, and it will give you this coordinate system warning. Essentially, it tells you that right now you have not defined the coordinate system for this raster. Do you want to do that? My recommendation is do it, because sometimes it's okay if you skip it, but if your basin is too large, it doesn't let you to delineate it until you have selected the coordinate system. So I'm going to select that. I know that my basin is in Indiana, and the UTM zone in Indiana is 16. So I'm going to click on predefined and select UTM zone 16 over here. And then set. There we go. So now if I click on over basin again and select my train data to terrain 1 and then save, you will see that the terrain data or digital elevation model will show right over here. All right, now that we have our digital elevation model, we need to do delineation. And delineation is essentially figuring out the sub-basins that are connected to each other to the outlet of our basin. Okay, so in order to do that, we need to go over the GIS tab. So if you expand the GIS tab, we already did the coordinate system step. I'm going to skip over terrain reconditioning. It's not applicable to what I'm doing right now. If you want to learn more about it, you can read about terrain reconditioning using the user manuals. Okay, next step is going to be pre-process sinks. Sinks are small depressions, small potholes that doesn't allow your watershed to have a dendritic river system. So we need to fill these sinks. Some of them are artificial, some of them are real depressions. So click on that. After a couple of seconds, you can see all of the sinks in your watershed area, in your digital elevation model area. Again, go back to GIS. Next step is pre-processed drainage. This step creates a raster that shows you all the little teeny tiny streams that exist in your watershed area or digital elevation area. Next step is going to be identify streams. So when you click on that, it asks for some effective area. The smaller the area is, the more details you're going to have in your watershed system, in your basin system. In other words, the smaller this number is, you're going to have more sub-basins created. I'm going to accept the default right now, but later show you how changing this number is going to impact the creation of sub-watersheds. So let's accept this. Remember, 0.21 was the default version. I'm going to click OK. It creates the system of rivers for me. So the lighter, essentially this is a flow accumulation raster. So the lighter yellow represents accumulation to that area, and the darker brown represents higher accumulation. Okay, so next step is going to be breakpoint manager. You need to have an outlet for your stream. If you know where your outlet is, you can select this tool over here, go to your watershed and click there, and that would be your outlet. I have a shapefile, so I'm going to go under GIS and click on Breakpoint Manager and import a shapefile that I have. My shapefile is called outlet. I'm going to select that, import, and you can see that the breakpoint is added. All right. Frequently save your project in case your computer freezes or you lose electricity, then you have access to your project. Okay, again, back to GIS, and last step is to delineate all these elements that we have added. It asks you what should be the prefix of subbasin. I'm going to say capital S. For reaches, I'm going to say capital R. I do want to create junctions and have the prefix of J. Okay, click on delineate. After a couple of seconds, you can see all the entire watershed and the sub-watersheds and the reaches. So if you expand this, you will see that you have S1, subbasin 1, all the way to subbasin 9. So 9 subbasins. How many reaches are 4 is the largest one. So 4 reaches and 4 junctions. The entire area of my basin is about 3 square miles. So it's pretty small. Having 9 subbasins for a basin that is only 3 square miles is an overkill. It's extra. So what if you want to reduce the number of subbasins? Okay, if you want to do that, remember I told you about stream definition. Let's go to identify streams, and it asks you, do you want to overwrite the data? Yes. Now we can select a larger number. Let's say that instead of 9 subbasins, I only want 3 subbasins. So you need to repeat this process until you have 3 subbasins. I've done that, and I know that if I increase this number to 0.5 square miles, and if I go ahead and delineate the watershed again, I will end up having 3 sub-watersheds. Let's do that. So I'm going to recalculate and redefine the streams. All right, and then I'm going to go and delineate the elements again. So it asks you the same questions. I'm going to S, R, and yes, and J. Delineate and continue. So after a couple of seconds, this time, you will see that instead of 9 subbasins, I have S1, S2, and S3. So 3 subbasins, 1 junction, 1 outlet, which is sink, and this blue line is a reach. So if I expand, 3 subbasins, 1 outlet, sink, 1 reach, and 1 junction. Okay, so This is how you define your watershed, your sub-watersheds, your outlet, and all the physical characteristics of your watershed. Now, the next step is going to be the definition of the methodologies and the variables that go into this physical conceptual model that you have defined. How do we define different variables? So when you click on any of these sub-basins and expand it, or you click on it, you'll see that first of all, it will be selected over here. It gives you some basic information about the sub-basin, and it allows you to set different methods that you want to consider for modeling that specific sub-basin. Okay, but before talking about that, let's make our view window a little bit cleaner. So what I want to do, if you want to check on or check off any of these GIS rasters or shapefiles, you need to go under View and then Map Layers. And then you can check on or check off any of these layers that you can see. For example, I do want to have my icon, sub-basins. I do not need the breaking point, and then I do want to have the identified, maybe I don't need the identified streams, don't need the accumulation, don't need flow direction, don't need the sinks, don't need this one, and I do not need the train as well. So this is a cleaner look that you can get. Perfect. So back to setting up the methodology for different subbasins, and then you can click on subbasin 2 and do the same thing for subbasin 2 or 3 or reaches that you have as well. However, this works when you have only like 3 subbasins or limited number of subbasins. What if you have 100 subbasins? Clicking through these one by one and setting up the different methods for simulation is going to be tedious. So there should be a better way of doing this, and there is. But before talking about that, I'm going to introduce you to this parameters tab. This is going to be very important for setting all the methodology and all the values and all the parameters for different methodologies. The first thing that I want to talk about is going to be your characteristics. This characteristics option item gives you different characteristics of different subbasins and reaches. Okay, I recommend whenever you want to see the characteristics of the all subbasins, select the basin model. So all subbasins and reaches and junctions are selected, and then go to parameters. Under characteristics, click on subbasin. And for each subbasin, it lists very useful values such as the longest flow path, such as the slope of the longest flow path, and other variables and other parameters that help you to calculate time of concentration and lag time, for example. And then once you do this and close this, you'll see that there are some shapefiles, lines added over here. These are the longest flow path and essentially your sheet flow line, your shallow concentrated flow line, and your channel flow that will help you to calculate time of concentration. You can actually go under View and Map Layer and see that these flow path lines have been added to your data as well. This data, wherever you save your files for HEC-HMS, you can go there under GIS folder. You can download these data and import them into GIS software packages. All right, back to our parameters and characteristics. Now you can click on the reach and also see all these different values for different reaches that you have. I only have one reach, so these are the values for the reach that I have. Okay, now let's set different variables, and let's set different methodologies for simulating this stream flow to this outlet. This sink over here, sink number 1, is the outlet of the watershed. And I have some observed flow at this point, and I want to compare the observed flow over here with the simulated flow. Okay, take a look at the methodologies that are right now selected. For canopy method, nothing. All the way to surface method, nothing is selected, which is good because we want to do an event model. Loss method, initial and constant is selected. We want to change that to SCS curve number. For transform method, or in other words, for unit hydrograph method, right now Clark unit hydrograph is selected. We want to select SCS unit hydrograph method. And for recession method, for base flow method, recession is selected, and we don't want any base flow or groundwater method because we are simulating an event, a direct runoff method. We're not simulating groundwater. So you can do this over here by clicking on it and change it to SCS curve number for each subbasin one by one. But we want to do it all together because that's easier. So I'm going to select basin and then go under parameters and then go under loss. Loss method is your surface runoff generation method. Right now is initial and constant. I'm going to go to change method and say yes and change this to SCS curve number right over here and click change. This will change the method for all subbasins. How do I know? Let's click on subbasin 1 and you can see that right now the loss method is SCS curve number method. I'm going to do the same thing this time for the transform method and change it to SCS unit hydrograph. There we go. I'm going to do it once more for the base flow method, and instead of recession, I'm going to have it over none and change, and then save. Now if you click on any subbasin, you can see they are changed to the methods that I want to. Okay, next is to set up the parameters and variables for these methods. For loss method, I need a curve number, I need an impervious area if I want to, or initial abstraction is optional. Okay, I know that curve number for this basin is about 79, so I'm going to select 79 for all subbasins as an initial number. But again, I want to do that for all subbasins at once, not one by one. The other thing that I need to set under transform is the lag time for these different subbasins, okay, and also the peaking factor, which I'm going to use the standard peaking factor. Okay, so I'm going to select basin 1, go to parameters, and under loss, click on SCS curve number method, and then a window will open like this, and it allows you to put curve number and impervious area and initial abstraction for different subbasins, 1, 2, and 3. Curve number, I'm going to set the value of 79 for all of these and apply. The impervious area, the area that I have is mostly agricultural, so I'm going to say that impervious area is 0 or very close to 0, and initial abstraction by default is 0.2 or 20% of the maximum watershed storage. I'm going to accept that, so I'm not going to input any values over here. Okay, apply and close. Going back to parameters under not this time under transform, I'm going to select SCS unit hydrograph, and I need to select the peaking factor and lag time. Okay, for different subbasins. What is peaking factor? Peaking factor will control the peak of your hydrograph. The default number is 484 in the original SCS curve number equation. However, there are different values that you can select. Let me actually expand this a little bit so you can see better. There are different values. It ranges from 100 all the way to 600 that you can select for your watershed. For different watersheds and subbasins, this value might differ. We're going to come back to this later, so remember this number. But let's put the lag time over here. So I have S1, subbasin 1, subbasin 2, and subbasin 3. The lag time for these, I'm going to say for subbasin 1 is going to be 70 minutes. For subbasin 2, I'm going to say 50 minutes. And for subbasin 3 is going to be 30 minutes. Okay, these are values that I know based on my initial calculations. I'm not going to go over these values, but there are equations that allow you to calculate rough lag times based on watershed characteristics such as slope and curve number and so on and so forth. So I have done that, and I have these initial estimates. Later, we're going to calibrate the model and change these values. So I'm going to apply that. Perfect. And now let's click on S1, subbasin 1, to check if the changes are there. So if I click on loss, you can see that curve number is 79, transform, there we go, the lag time is over here. Perfect. The other thing that I need to do for the reach, I need to select the lag time for the reach flow as well. So because I only have one reach, I can set the lag time right over here, and I'm going to put the number of, let's say 30 minutes. All right, so I have everything. now I need to, and this is my sink, I don't need to input any information for the sink because that's the outlet of the model. Okay, so this is how you define your hydrologic model and different methods to simulate the outlet flow or stream flow at the outlet, which is sink 1 over here. Now that we have our watershed set up and the methodologies have ready, what we need to do is to create some sort of forcing inputs for our model. In other words, we need to define our rainfall, our event, right? So in order to do that, again, I'm going to go under Components and click on the Meteorologic Model Manager and create a new MET model. I'm going to call it MET1, and it will show up right over here. When you click on it, it tells you what kind of data you want to enter. By default, most of them are none except for precipitation, right? And the unit is US customary system of units. One thing that I recommend is changing the replace missing value to set to default. So by default, sets all the missing values to 0 instead of stopping your runs. Okay, so there are different ways of doing the precipitation or defining precipitation over here. In the previous video, I showed you how you can define a hypothetical storm based on the return period of a storm. But here, I'm going to specify a HEC-graph. A HEC-graph is a graph of rainfall over time. So I'm going to specify the HEC-graph. So let's save this. On the next tab, basin, it asks you, do you want this MET model to be connected to any basin? Yes, we want this to be connected to basin 1, right? So we need to change this to yes. And then the option model over here, we don't need to change that. The default is good for us. Okay, I'm going to save this. Once you have selected specified HEC-graph, it shows under MET1. So if you select that, now it will give us the option of selecting or putting the data for this. You can see for different sub-basins, S1, S2, and S3, there are no gauges. These gauges will give us the HEC-graph, the rainfall data. So this is telling you that you need to define a gauge and then come back over here and connect that gauge that you have defined to different sub-basins. So I'm going to do the same. Under Components, I am going to click on Time Series Data Manager and define a precipitation gauge, right? Okay, I'm going to set New and then call this capital P Gauge 1. All right, create. This is going to be my precipitation gauge. Expand time series, expand precipitation gauge. Click on P Gauge 1. I'm going to manually enter the data. Okay, the units of my precipitation is going to be incremental inches, not millimeters. And the time intervals of my data is 15 minutes. Okay, so this is the data that you need to change. Click Save. And now you can expand P Gauge 1 and define a time series and define your data. Okay, click on that. My simulation is going to be from April 4th, 2011 from 8:30 a.m. all the way to April 4th, all the way to April 6th, 2011, and the time would be 8:45. This is the time that I have data every 15 minutes on. Okay, then click on Table. There is automatically a table over here that you need to populate based on your precipitation. So I'm going to go to the other screen that I have and copy precipitation value. You have access to that as well. It's an Excel file with the files. I'm going to copy and paste it right over here. You can see that all these precipitation values are populated. And then click Save. There we go. Okay, so these are the precipitation values that I have every 15 minutes. And then if you click on the Graph tab, you can see a graph of precipitation. I only have precipitation for the first portion of this time period. All right, I'm going to save that. Okay, so this is how you define your gauge, right? Now remember, you need to go back to a specified HEC-graph and then connect different sub-basins to the gauge, to the precipitation gauge that you have create it. Okay. Now that I have this, I can put the observed value of discharge for the sink as well. Okay. So remember, the goal is to generate the hydrograph for this sink, for the outlet of the watershed, and compare those values to the value of observed stream flow at the same point, okay, to see how your model is done. I'm going to go under components, again under time series data manager. This time, instead of a precipitation gauge, I'm going to define a discharge gauge, and I'm going to call it capital D gauge 1. Create. Okay. Again, discharge gauges show up over here. Same process. It will ask you, how do you want to enter your data manually? What are the units? My units are cubic feet per second every 15 minutes. Save that. Expand it, click on it, and define a time period. Same thing. 04 April 2011. The time that I have is going to be 08:30 in the morning to 06 April 2011, and end time is 08:45. All right, go to table and populate your discharge in CFS, cubic feet per second. Again, I'm going to copy from Excel file that I have and paste it right over here. Notice that instead of 0, I have a very, very small value. Sometimes this helps you to get less errors and warnings in HEC-HMS. So you can start from 0 and see if you get any errors or warnings about missing data and change this to a very, very insignificant value. Okay, so now we have our discharge value, but we need to tell HEC-HMS that we want these values to be compared with the values that are simulated at sink 1. So I'm going to select sink 1 and then go to options, and under observed flow say yes, I have observed flow and the values are saved in capital D gauge 1, the discharge gauge 1. Save that. All right, so now we have defined the forcing input data and our calibration data, the discharge values for our watershed. The other thing that we need to do, go to components, and the last step would be defining a control unit. If you click on this control unit, new one and control 1, the purpose of the control specifications or unit is to define the time span of your simulation. Okay, again, 04 April 2011. HMS loves to ask you to input this data multiple times. So this is not the last time that we're going to write the simulation period for our simulation, for our hydrologic modeling. 2011 again. All right. This simulation that you enter in the control specifications does not have to be exactly the same as the intervals of your input data. In other words, you can have 15-minute rainfall or 15-minute discharge, but you can run the model every 30 minutes or every hour, so on and so forth. So this doesn't have to be 15 minutes. You can change that if you want later. I'm going to keep it 15 minutes right now. Okay. We have our control specifications. I'm going to save the model. And next, we are going to create a run and run the model. The next tab that we are going to work with is going to be compute. So when you click on compute, you can click on simulation run manager and create a new run. We're going to call it run 1. These will help you to have different scenarios. Why? Because when you click next, it asks you what basin you want to select. If you have multiple basins, you can select that. What input data, what forcing input data you want to use. We want to use whatever we define in MET1. And what control periods. Let's say that you want to have a 15-minute simulation and a 30-minute simulation and 1-hour simulation. So you can have different control specifications. But we have one, so we're going to create one run and then close this. So that will show up if you change your tab over here from components to compute. That will show up under simulation runs and run 1. Okay, this will give you some information. To run the model, you need to right-click on this run and click Compute. And sometimes this happens actually, and the model doesn't run. So you need to closely read the error and warning messages that you have over here. So the error message that I get is that simulation end time, April 4th, 2011, is not an even number. So immediately I know that my end time is not April 4th, it's April 6th. So I'm going to close this, go back to components and control 1, and there we go. So instead of putting April 6th, I mistakenly put April 4th. So I'm going to change this to 6th. There we go, and then save that. And double check over here. This is April 4th to April 6th and April 4th to April 6th. Good. Now we should be good to go. I'm going to go back to compute and right click and compute again. Okay, so you can see that our simulation run is done. We got 2 warnings. These 2 warnings are about the simulation time intervals. So HMS recommends that the simulation time interval should be less than almost 0.3 times lag time for sub-basing. Ours is larger than that. This is HMS recommendation. You don't have to follow that recommendation. You need to take a look at your results first, right? And based on that, if you think it is proper for you to decrease your simulation time interval, you can do that. In this demo, I'm not going to do that, but because you have the data, you can actually decrease the time interval of the simulation and see what happens later. Okay, I'm going to call this good, and then go under results and expand simulation runs and click on run 1. You can see the results over here. You can play with all different tables that it will give you and the calibration summary that we don't have right now, and click on different sub-basins, but I'm going to click on sync 1 and then click on the graph just to show you the hydrograph. The blue solid line is the simulated hydrograph, and the black line is your observed hydrograph. You can see that there is a very distinct difference between simulated and observed hydrograph, and that's expected. No hydrologic model is going to be good at first, so you need to do some calibration. But instead of beginning with auto calibration, I want to highlight that you need to start with manual calibration. As a hydrologist, as a civil engineer, as a hydrologic modeler, you should be able to understand how your model behaves. For example, you can see that right now the simulated peak is way higher than the observed peak. This is telling you that you need to moderate the peak value of your simulation. And that's done using the methodologies that you have used for generating hydrograph. Remember the peaking factor? And I told you that the original number 484 is usually too high. So if you want to do manual calibration, you should go back and fix that. So what I'm going to do, I'm going to first of all save this, go back to components, select my basin model, go under parameters. My transform model is my unit hydrograph model. Click on SCS unit hydrograph and then manually change the peaking factor over here. So I'm going to change the peaking factor from 484, let's say, to 151 and see what happens. So 150 and 150. I'm going to apply. There we go. And now you can run the model again using this change run. So click on it and compute. It is done. Okay, I'm going to go to results and then click on graph over here. Now you can clearly see that the peak of the simulated model is very close to the peak of observed hydrograph. Okay, this is good. You can go on and change the curve number values to see what happens. But instead of doing that, and this is how you should do it, but because this is just a demo, I'm going to move to auto calibration right now. Once you have your run, then you can create an optimization model to try different parameters and find the optimized value of these parameters for you. What are the parameters? Curve number was a parameter, a lag time was a parameter, and so on and so forth. So I'm going to do that. So under compute, I'm going to click on Optimization Trial Manager and create a new optimization model. I'm going to call it Optimization 1, and then using Basin 1, Met 1, create that. Okay, so again, under Compute, Optimization Trial is right over here. Let's click on it. There are certain things that we need to define over here. Again, HMS loves to ask about the start date. This time I'm going to put it right. It's April 4th to April 6th. The start time is going to be 8:30 in the morning all the way to 8:45 in the morning on April 6th. Time interval is going to be 15 minutes. I'm going to save that and then copy this value, because I know when you go to the next tab, which is search, it's going to ask you about the iterations or the number of trials that it does. This is good for now. I'm going to come back to this, and if you go to objective, it's going to ask you for the start date and end date, which I need to change to April 6th, and the time and the end time. Okay, let's talk about this. What is the objective that we're trying to achieve? We want to compare our observed hydrograph with our simulated hydrograph and minimize the root mean square errors. Okay, so it's going to, at sync 1, compare the simulated value with the discharge value and minimize the root mean square error. If your objective is to minimize the error in the peak discharge value, you can change this to % error in peak discharge value. But let's run it with root mean square error first. Okay, I'm gonna save that. Go back to search. There are different methods of optimization. Simplex method is a simple method that you can use. It goes through different parameter values to find the best of them. The univariate only optimizes one variable, and the differential evolution is the most complex value that uses a statistical method to find best values, best parameters for the model. I'm going to start with the simplex method, okay? And I'm going to start with 100 iteration. That should be good enough. So I'm going to save this. Now you're going to ask me, how do we define the range of the different parameters that we want to optimize? And in order to do that, you need to right-click on optimization and then add parameters. So I'm going to add different parameters. When you click on parameters, you can, let's say, usually I do it for each sub-basin and each reach separately, not all sub-basins. So for sub-basin 1, I'm going to optimize curve number, and the initial value that I defined was 79, right? But I wanted the minimum to be, let's say, 65, and the maximum to be, let's say, 85. How do I know these numbers? I know the watershed that I'm modeling, so I have some information on it, and I know that it's an agricultural area, so it's not going to have a 99 curve number realistically. So I'm going to save this, and if you want to add, remember this was only for sub-basin 1, so you need to add more parameters for different sub-basins. Again, sub-basin 2, curve number from 65 to 85. And I'm going to do the same thing for sub-basin 3, curve number 85. Okay. This was only for curve number. Now you can add more parameters by clicking over here. And let's say for sub-basin 1, instead of curve number, you can add lag time over here too. The original lag time was 70. You can change it to the range that you think it would be, and add all these parameters for different sub-basins as well. I'm going to pause the video, add all these parameters over here, and then come back and show you how I've set it up. Okay, in total, I have 7 different parameters that I wanted to be optimized. Optimized to give me the most similar hydrograph to the observed hydrograph that I have. Okay, let's save this. And then in order to run this optimization, you need to right click on it and click compute. And it will compute multiple iterations to give you the optimized parameters. And you can see the number of iterations over here. Depending on your computer, it could take a couple of minutes. Okay. Now that we have this, I am going to go over results. Just to remind you how results look like for our run, I can show you the graph. So this was how a result looked like before doing optimization, right? And then we did optimization. Just to show you how that will look like, you need to expand optimization trials, click on optimization 1, and then you can go over, first of all, you can take a look at this table that gives you what was the initial value and what was the optimized value, okay? And then you can click on the sync and click on the graph. Now, this is the optimized value. You can clearly see that the model is doing right now is doing better in the descending part of the hydrograph, the falling limb of the hydrograph, but the peak is not matched anymore. Okay, so you need to decide if the peak of the hydrograph is more important for you or the general shape of the hydrograph. Okay, now let's go back to compute and click on optimization and then click on objective. This time, instead of root mean square error, I'm going to select percent error in peak discharge. So in this case, having a better peak discharge is more important for me. I'm going to save this, right click on optimization and compute, and wait for a couple of seconds. All right, go under results, and now let's check the graph again. Now you can clearly see because having a better peak was more important for us in the second run. Now the peak is very close, but the general shape of the hydrograph is a little bit off. You should pay attention that there is no model that can give you the exact shape of the hydrograph, and if that model exists, your model is over-calibrated. Remember that you calibrate your model to use it for other similar rainfall events. If your model is over-calibrated, then the validation process is not going to be correct as well. So this was the simplex method. Let's go back to compute and click on optimization and the search method. Instead of simplex method, you can use differential evolution method. When you click on that, you can see that there is a value called seed value. This is a random value generated that shows you this method is stochastic. So it's going to have a population and randomly assign different parameters to find the best parameter for your model. Okay, I'm going to, first of all, change the number of iterations to 200. Usually, differential evolution method requires more iterations than the simplex method, but I'm not going to change anything else. I'm going to go to objective though. Instead of having the percent error in peak discharge, I'm going to change this to something else. You can use the Nash-Sutcliffe efficiency method or any of other these statistics that you have over here. I'm going to simply choose the root mean square error or R squared. I'm going to minimize that, okay? So save that and run the optimization. It's going to take a while, so I'm going to fast forward this video and come back and show you how the results are going to look like. All right, the simulation is done. Let's take a look at the results. I'm going to go to the Result tab, and just to remind myself, this is how the original run looked like. We'll see if after optimization, this blue hydrograph is going to be closer to the black hydrograph, which was our observed hydrograph. So let's go back to optimization and under sync graph. So you can see that definitely this blue hydrograph using the new optimization model, the differential evolution, looks closer to the black one. Now, it comes to your engineering judgment if all these parameters make sense. So if you click on it, you can see that stochastically it has tried many, many values for parameter 1 was curve number for sub-basin 1 or other parameters. So you need to click on the optimize parameters and compare these parameters, the optimized values, and see if that makes sense for your watershed. If it does not, you need to change these values to see what makes sense. Remember, the goal is not to get a simulated hydrograph that is exactly similar to your observed hydrograph, because that's overfitting, that's over calibration. You don't want to over calibrate your model because you're going to use that model to simulate similar rainfalls for other watersheds, right? That's the importance of your engineering judgment. For example, by looking at my essentially optimized parameters, I can tell that the value of 85 for sub-basin 1 might be a little bit high. So I might go and manually change this value instead of 85 to something lower. Okay, so this was a short introduction of optimization in HEC-HMS. Let me know in comment section if you want me to create some more in-depth videos on optimization or other topics related to hydrologic modeling.